If you've been following along with our discussion about interrupts, well, you know that interrupts improve the performance of I/O by not requiring the processor to keep checking if I/O has something to say. We can make it even better. In episodes 69 through 71, we talked about interfacing memory to the bus. And so we had some sort of a group of wires, right? And there are three groups of wires. There was address that allowed us to identify which memory location we were trying to communicate with. And there were data lines that allowed us to pass the actual data back and forth between memory and the CPU. And then there were control lines which controlled that process. And so we had the CPU that was communicating with memory, right? But beyond that, we also had I/O connected to this bus. All right, input and output. And that was really when we started our discussion with communicating with I/O. Now, remember that polled I/O meant the CPU set up the I/O and then had to keep checking back with I/O to see if it had something to say. We removed that responsibility by saying, okay, CPU is going to set up the I/O device, and then the I/O device is going to have enough intelligence to perform its operations and then alert the CPU through an interrupt to say, hey, I got something to say, or I'm available for whatever process that you needed. All right. The problem is it doesn't quite solve all of our problems, because let's say that we've got a large block of data, maybe one of these I/O devices, maybe it's a network interface card or a hard disk or a solid state drive, something that its job is to grab a large amount of data and then have that large amount of data move from the device into memory so that the CPU can operate on it. Okay? So that means that the interrupt service routine ends up being something like this. Well, it's a large data transfer. And how do you do a data transfer? Well, let me go down to the assembly language level. I realize that this is not an assembly language class, but to get an idea of what the CPU is doing, let's take a look at some of the assembly language commands. So we have LDA, R0, and then R1 in brackets. Let me explain what this instruction is doing. The register name, so these two are registers. Remember the top of the memory hierarchy. These two are registers. Now the one that's in brackets means that instead of using a piece of data in that, we're treating that as an address. And so R1 contains the address that we're reading from, we're loading from. And so maybe if we're receiving a large message from a network interface card, it's pointing to the address of the network interface card's buffer that allows us to bring in that data. So it's pointing to the address inside of the I/O device. And then R0 is bringing that data into the CPU. So we've got a read from I/O into the CPU. Now, the second step is to take the data that we just read and store it. So we're going to store R0 to what R2 is pointing to. All right? Now, R2 is probably pointing to an address in memory. So we've got one read into the CPU and then a write from the CPU. Now, this has got a couple of problems. Problem number one, each data transfer or each data element transfer requires two memory cycles. All right. So I've got one data element. How many times did I have to access the bus in order to move that one data element? I had to do it twice, a read and a write. All right. So that's one problem. Now the second problem, though, is that it monopolizes the CPU. So during this data transfer, the CPU is having to do rather trivial operations. I mean, these are not high-end floating point multiplications or anything processing. We're just moving data. Wouldn't it be cool if we could get something else to handle that transfer for us? Well, it turns out that we do. We can create a fairly simple processor referred to as a DMA, or a controller. And DMA stands for Direct Memory Access. So we've got this little processor, and it doesn't need to be all that complicated. I mean, think about it. To do this transfer, I needed 3 registers. I needed 1 register to show the address of where I'm reading from, one register to contain the address of where I'm writing to, and 1 register to contain the data. That's it. All right? Now, what happens is that the CPU will tell the DMA, here are the details of the process. I need you to read from this I/O device to memory. Or maybe we're sending a message through a network interface card. So the CPU might say, I am going to ask the DMA to write this block of memory into this I/O device. Now, notice we got a problem. There's now 2 processors trying to work on this bus. They can't both be using the bus at exactly the same time. So the CPU has to stay off the bus long enough for the DMA to do that transfer. We're going to talk about some of the ways we can solve this problem, but let's take a step first. Let's see what the DMA has solved so far. So far, it has solved the problem of the step 2, monopolizing the CPU. Let's see if we can't figure out how to solve the problem of step 1. Now, it's pretty simple hardware. It's a pretty simple processor that's going to allow us to do this transfer. But what does the CPU need to do in order to get the DMA to do its job? So, to control the DMA, a processor must, or the CPU must, first of all, we've got to tell it whether it's a read or write operation. In other words, what direction are we going? Are we going from memory to the I/O device, or are we going from the I/O device to memory? Going back to something simple like some sort of a storage device, like a hard drive or a solid state drive. If I'm storing a file, you have to tell the processor that we're writing to I/O. If the storage device has read a file and it wants to be brought into memory, we need to tell the DMA that that's the direction that it's going. All right. We need to tell it the address of the I/O device, right? So and once again, this I/O device itself, it may just have a specific single address that it's going to be passing everything back and forth to, or it may have a block of addresses, and we know whether we're incrementing through that block to bring it into memory, or if maybe we're just reading that same memory location and making multiple reads to be stored into memory. All right. Then we also need the address, and by the way, both of these addresses are going to be starting addresses, the initial address where we're going to start this block transfer of data. So of memory that we're accessing, all right? And then the last thing is the size of the block to transfer. Those 4 things are enough to get the DMA started. All right. Now, that doesn't take much of a complicated processor, but it does mean that the DMA is going to need to monopolize the bus. I mean, think about it this way. If I've got the CPU reading from memory in order to execute code while the DMA is doing a transfer, those address and data lines are going to be, well, they're going to have contention. It's called bus contention, where these, we've got 2 different things trying to drive the line or access the lines at the same time. That's a problem. So what the processor does is it allows the DMA, it backs off in order to allow the DMA to access the bus. That's called cycle stealing. Let's talk a little bit about that next. So, what does the DMA need to do in order to get the CPU to let it use the bus? Because the CPU should be in control of the bus and be the one to allow permission for the DMA. So basically what the DMA does is whenever it has found, and it usually does this through some sort of a connection to the I/O device, that the I/O device has something to transfer. And the DMA says, oh, I've got to transfer something, I need the bus. So what the DMA does is it requests the bus from the CPU. All right, some sort of a thing called a hold request. There's a number of different names for it depending on the hardware you're using, but a request from the DMA to say, I need the bus. Now, the CPU then acknowledges the request. It does this by doing something called tri-stating the bus. All right, now what does it mean to tri-state a bus? Well, in Boolean, we haven't talked much about tri-stating, but in Boolean, how many levels do you have? 2, right? 0 or 1. A third state means that it kind of disconnects it. Usually this is represented by a Z, the letter Z. And in electrical engineering type or electronics type nomenclature, the Z means high impedance. It's like an open circuit. It just basically means I am disconnecting myself from the circuit. So that's the third state, the tri, right? And so the CPU acknowledges it by saying, okay, I'm going to give you a signal saying I've acknowledged that you can have the bus, but I'm also disconnecting myself from the bus, all right? And then the DMA takes the bus to transfer the data, or more specifically, the data element. Now, this is not an interrupt. We're not calling any sort of interrupt service routine. You know, the DMA, this request, it's done through hardware. The CPU is not changing its mode. It's not changing the code it's executing. It's not stopping the code it's executing. It's just simply a hardware thing that allows us to go through this process to allow the DMA to have access. And then the DMA releases the bus and the CPU can take control of the bus. Now, this does slow the CPU's processes down, but we have kind of something we've already talked about that allows the CPU to execute code while the DMA has seized the bus or is stealing the bus. If you remember, at the very top of the memory hierarchy, we have registers, but right below the registers, we also had the RAM cache. All right, so we have the CPU. Now, the CPU actually is executing out of its cache, not directly out of memory. And if you go back to episode, I don't know, when we were talking about the caches, you recognize that the CPU makes a request to the cache, and the cache makes, if it does not have the element, the either instruction or piece of data that the CPU is looking for, it makes a request to memory and a block is brought in. All right? So, during this period of time, while the DMA is stealing cycles from the CPU is not necessarily stalled. It probably is executing code still just fine out of its cache. All right? Means that we really are only slightly, you know, if for example, we do have a cache miss, which meant the CPU requested something from the cache that wasn't there. If the DMA has taken control of the bus whenever there's a cache miss, yes, we are going to have to stall the process on the CPU to wait for accessing it, wait to access memory. But for the most part, we should be executing out of our cache, which means cycle stealing shouldn't have that great an effect. Now, We've talked about solving the second problem. The second problem was the fact that the data transfer, which is a really simple operation, was really monopolizing the CPU, taking time that the CPU could be doing more important things. But what about that first problem? The first problem, where we are accessing the bus twice. Well, let's see if we can't solve that one too. Now, one of the ways to solve the problem of accessing the bus twice for every single data element we're moving, well, could be to purchase I/O devices, such as a hard drive or a solid state drive, that actually include their own DMA. And by doing this, what we've got is the ability to have the DMA do a transfer back and forth, reading and writing to its I/O device through its own bus, through its own very close interface. And then the communication with the memory just takes a single bus cycle. And so whenever we're doing a block transfer, in this case, when the DMA is associated with its own I/O device, then what happens is we have a single bus cycle used for each data element that we're transferring. Now we actually have another solution that could be done. By doing an interface through a DMA, instead of going to a single I/O device like a hard drive or a network interface card or something, instead connect it to an I/O bus and then have all of your I/O devices hanging directly off of that bus. And so in the case of having simpler I/O devices, we could just simply have a bus. For example, maybe a USB, maybe a USB hub, or some sort of another type of network interface. What you could have is all of your I/O devices hanging off a separate bus that the DMA communicates with. This would allow us to have a single memory cycle stolen for every single data element that we're transferring either to memory or from memory. All right. Now, this is all cool in terms of transferring large blocks of data, but it turns out that DMAs are also used for some rather unique applications. For example, picture this. Maybe I have an array of LEDs. All right. So I have, a small matrix of LEDs. And I want to send a pattern. I want to make this pattern that the LEDs go through. Maybe it's one of those little personal devices that has a ring of colored LEDs. And what I want to do is I want to send a pattern so it'll make a swirl in one direction or a swirl in another direction, or maybe they'll all dim and all get brighter. Well, what I can do is I can create in memory an array of values, the things that are going to set our LEDs to different patterns of ones and zeros, to different colors. So maybe I've got 12 LEDs and each one of them is an RGB LED. And so each LED has 3 binary inputs, one to control red, one to control green, and one to control blue. And what I'm doing is I'm going to turn those on in different patterns. Well, 3 bits for each LED for each of my 12 LEDs will give us 36 bits. And so what I'll have is an array of these 36-bit values. And then what I can do is have the DMA read through the array. Read through the array of each one of these different data elements that I'm sending to those LEDs in order to cause a pattern to go through. So now what the CPU can do is, in addition, and maybe we might have to have some sort of a timing defined by the DMA, in the DMA, and have the CPU define an array in memory, have this array of LEDs be connected to the DMA, and then the CPU simply says, hey, DMA, will you transfer from this address in memory to this I/O device, also referred to through an address, and simply go through that list and make it so that those patterns can be sent to that LED, and then the CPU doesn't even have to do any processing at all. It just simply hands that task off to the simple processor of the DMA. All right? So there are a lot of really cool things, or very important functions, that the DMA provides. You know, we talked about solving a couple of problems. One of the problems being that the bus is being used twice per data element that's being transferred back and forth between I/O and memory. Second was how much time it takes from the CPU in order to create or implement this transfer. The DMA solves the problem of monopolizing the CPU and cuts the number of transfers on the bus in half.